In this video, we're going to talk about some exploratory analysis of sequences using visualizations and using descriptive statistics that we can derive from sequences. As we have already demonstrated in earlier videos, you can generate plots from sequence data you create using TrialMiner. And the main function you use for that purpose here for generating those sequences or visualization of sequences is called SEQI plot. This is a particular type of plot that I stands for that's type of plot. And there are other types of plots you can create in TrialMiner, right? And here again, using the data set we used before, using the log data from PennGSE. And here we want to plot the first 20 sequences instead of the first 10 sequences. You can feed the number or the indices in the sequence data set to this function. And here we have the plot that captures the first 20 sequences. And here you already see, we only started with the first 10. Now we have a few more that we can plot in this new attempt, right? Beside this simple plot of what each sequence contains, we can also plot. There's another type of plot called state distribution plot that can be created using TrialMiner, right? And then this is the function for creating this distribution plot. Here, the D stands for distribution plot, and it provides you a graphic that shows the state distribution at each time point. And here, again, the x-axis is each time point, and it keeps going until 100 because we set a limit of the length in the plot to be 100, right? And how to read the plot, and it's pretty straightforward. As you see, every player starting the level, right? So you see this is 100% for the first second. It started with this start state. And then as you move on, some still have the start and some moved on to something else, such as key press. And for this data set, you can see the key press is most dominant state for after you start the game, because that's very typical, right? And the player has been mostly pressing the key, right, in this specific situation. But interestingly, as you get into some, later second, starting from maybe around 10 seconds or so, you see some other colors that is about removing the rule. As if you recall the level design, the player need to remove the rule to get out of the box. So, you see a lot of players starting to conquer that milestone around this time. And you see a lot of diversity as you get into the later part of the time session. And interestingly, there are a lot of undos around this 66-second time period across those different sequences, right? It means that the player maybe at this point of, after the 1 minute mark, a lot of players are bumping into some troubles. That's why they're trying to do a lot of undos to rewind their play process to maybe come up with a different strategy and so on. And there's other kind of little boxes that stand for adding a rule or being idle for a moment, right? You see some kind of idle that stands for long pause, a different time period of the game. So even with this simple plot, we can start to observe some interesting patterns for this level and for this game. And you can do the same for your own project using TrialMiner to achieve the goal, right? Again, this is another plot, which is called state distribution plot. Very popular, very useful to get a sense of the data set you have. And there are other types of plot you can encounter as well, but for this video, I will mostly talk about those two plots. I think that most useful, very useful, but there are some useful plots you can dive into as well. If you take a look at the manual I mentioned earlier about TrialMiner, you can find more. right? Another part I want to get into in this video is, besides plotting, you can also think about coming up with some additional information that can help you describe, it can help you describe the states, and also help you using numbers to characterize for each for each state, how frequent they are at a particular moment, right? Here, beside using this visualization we see here, you can also use numbers to summarize or help you describe at which point how dominant a state is, right? So this is basically the same information, same data as the plot you saw, but it's using a numeric format to represent that information. And here you see this is, using this function that is about the stats, right? A stats table that to summarize the information. And using this function, you will print out this table. We want only the first 5 columns, the first 5 seconds, basically, for this data set. And you see the start state is making up 100% of the first second, and the second seconds includes start and also include the key press as well. And then if you move on, you see the key press continue to be dominant, but there's some other types of states that comes into play in later seconds, right? Again, this is showing you the same information. Instead of using the plot, we're using this kind of tabular format to demonstrate how dominant each state is in a particular time moment. And other plots in this TrialMiner, there's another plot if you think it's pretty interesting to look at as well. It's called this sequence frequency plot, and using this function called seqf plot. It's this, F stands for the type of plot. This plot shows you the most frequent sequences, and by default, the 10 most frequent sequences are plotted. You can adjust this with how many you want. You can want the first 20 plots, the first 20 frequent sequences in this data, and they order by decreasing frequency from the bottom to the top, and the bar width stands for the proportion of that sequence frequency. So here's one example, right, using the same log data, and you see in this data set, the 10 most frequent sequences are those, and the bottom one is most popular. And what this is you see after this starts, there's a long sequence of missing data. That means after this session start, the player didn't do anything for a long time, and I'll be wondering why. It could be the player left the computer, or it could be the player has been thinking, could be the player has been doing something different or answering the survey or something like that. So I have no idea. But this could be something by pulling out the most frequent sequences from the data set, you can start to see what are the most frequent sequences in the data. And the same, as you move up, you see the width of the bars, or the height, I should say, of the bars is reducing. That means those are less frequent than the first one, but they're still frequent for this data set. And you see a range of them, and together they are making up 7.1%. So all of them combined are appearing in 7% of all the sequences in the data set. So by looking at this kind of sequence frequency plot, you can start to see the most dominant sequences in the data set, and maybe you can filter something out if that's important for you, right? But this provides a different view than the first 2 plots you saw, either this direct visualization of the sequences or this state distribution plot, and this sequence frequency plot provides you a different view about this data set. And similarly, you can also plot that information using a different format. Again, this is the same information, but you're printing that out in this text format and describing this in a way that's following the state prominence format more closely, so that you can look at this differently. Another angle to think about sequence data is to talk about the transitions. Transition means, if you recall that in the trial minor terminology, there's a state, there's an event, and transition happens when an event, right? It's basically about the events. When you change from one state to another one, that's a transition, right? So there's a function called seq trate that computes the transition rates between different states. And the outcomes is a matrix, right? It's pretty straightforward because you are moving from one state to another, and so the matrix captures how you're moving across different states. The distributions, right, of how this transition happens, they're starting from t to t1, t plus 1, right? That's summarized in this table. And if using the same data set, again, we can use this function to come up with this transition matrix. And here in the matrix, the rows is where the state is at t, and then columns are the state at t plus 1, right? So for example, if we come up with, look at this row, we can see that in the play, the play session never start from start and then right away move into end, and never start from start and then move into idle. It's most likely the player start the session and move into key press, right? So we can see a pretty direct information about how the players are moving across different states. And you can see the key press, because it's so prominent, you can see it connects with other types of states by looking at the column that correspond to key press. So again, this transition information helps you take a look at how different states are shifting among each other. And this is not a visualization, but it provides you some basic numeric information to describe the transitions. And the next type of information you can get from trial minor is to think about average time spent on each state. You can plot this similarly using this plotting function. And here I want to mention a little trick. You can either use this function, which is seq_mt_plot, or you can use this generic function, seq_plot, and feed the type as a parameter into this generic function to achieve the same goal. So basically, you can use this function and ignore this part, or you can use this generic function and type and feed this parameter called type equals mt to achieve the same function, same goal as this one. And this applied to earlier plotting, including the I plot and the frequency plot as well. You can use a generic function and add another parameter to get the same plot. But here, what this average time spent on your state plot is getting, it provides you on average how much time is spent on each state across those sequences. Again, you see key press is very dominant. It's less dominant or less represented in the data set. And if you use a different data set, you might get a much more interesting picture. But this is how you can provide a very high-level description of the frequency of the states. And there could be more, right? Besides how long this could be about the states, another angle to look at the sequences is you can think about how the length of the sequences is distributed. I remember the shortest one is 12, seconds. The longest one, 3,600 seconds. So there's quite a long distribution or of this data set. So we might want to take a look at how the length of the sequence look like overall in this data set. And the way you do that in this using TrialMiner is you call this function called a CPU length. You feed the data, the sequence data in, and then you will try to plot that information using the histogram of the base R package. And here's the outcome. You see, most of the sequences are shorter than 500, right? This is 500, mostly they're short, and there's some that's a bit above 1,000. There are some rare cases that's more than 3,000 seconds. I should remember this is a mistake. The sequence length in seconds, not in minutes. So, but this is how you can, take a look at the length of the sequences so that you can make informed decision about how to treat your data set. And there's more you can do with TrialMiner. We're getting into some additional information. The purpose of doing all of this is to kind of answer this question, how we can leverage TrialMiner to extract meaningful information about our sequences so we can do some other things about the sequences, right? Another thing you can do is to come up with the distinct state sequences using this function, which basically compress. You remember those key presses they're repeating, but in the same time, if you can compress them, if you kind of merge those same repetitions, you can come up with some distinct state sequences using this function. So I don't want to talk more about it. You can play with it if this matters for you. In some cases, you don't care about the length or how a specific state will continue. You care more about how different states move across each other. So that's when you might be interested in looking at the distinct state sequences versus the typical sequences of the states. And there are other ways to, to describe those sequences. I want to introduce two interesting statistics that people have used to describe the sequences, because we can talk about the length, we can talk about the distinct number of states in the sequence, and there are also other way to, for example, to talk about how rich information there is in a sequence, or how stable, right? How much transition happens in a sequence. So there are two different statistics that you can use, at least. There could be many more, but those are two that I think will be interesting to look at in this case. The first one is a very popular concept called Shannon's entropy. And here's the function you use to compute Shannon's entropy. But in the TrialMiner package, entropy can be interpreted as uncertainty of predicting the state in a given sequence. If all 6 states in the sequence are the same, the entropy will be equal to 0, and it is maximum when the cases are equally distributed between the states, right? So that's Shannon's entropy, and you can use this function that will return the normalized entropy about the sequences. Remember, we have those different sequences, and here we're plotting from the 31 to 41, those sequences, again, using this type I plot. And here we can compute using this function that returns Shannon's entropy about those sequences, because we're so tired of the first 10, so that's why we're coming to look at those different sequences. And here, this is normalized so that it has a more comparable number to look across different sequences. And you see the number of the value of the first sequence is 0.15, the next one 0.09, right? So it tells you how those sequences are different in this case, and there's some more higher value sequences that's part of this data. We can also plot this Shannon's entropy using the plotting function here for the whole data set, right? We just looked at 10 here. And here's if you look at all the sequences in the data set, you get a distribution of the Shannon's entropy across those sequences. And so I'm going to skip a few additional things we're doing here. Basically, you can do all kinds of descriptive analysis of the statistic of Shannon's entropy after you have that, right? So here you can come up with how it's distributed, the quartiles, and so on, and then after you group them, you can plot. You can plot the frequency plot for different segments of the sequences. That's where I think it can get interesting if you come up with a particular cut point based on the statistics, then you can start to plot the sequences of each segment. And here we're plotting the first 55% and or lower, or 55% and 90% or above 90%, just to see how those different segments defined by Shannon's entropy may look different for this data set. Right? This could be you have different cut point for your own project, right? There's no right or wrong cut points. Again, the decisions are made by the theories or made by you who know this context, who know the data. But it provides you a way to dissect or slice the data set or the sequence data so that you can look deeply into different segments or different slices of the data to answer some interesting questions. Another, similar to Shannon's entropy, another statistic I think will be interesting to look at is called turbulence. Turbulence, it depends on the length of the sequence. It's based on the number of distinct subsequences that can be extracted from the distinct state sequences and the variance of the consecutive times that's spent on the distinct states, right? So it's basically intuitively describes how turbulent that sequence is. And then you can remember this is those sequence we looked at earlier as we look at Shannon's entropy, and we can do the same. We use this function, seqst, right, to pull the turbulence statistic from that the same sequence here, and we can do the same for the Shannon's entropy together, and then we combine them into a data frame that has two columns. And here's the outcome. For those sequences, you have this column about turbulence, another column about entropy, and you can start to do other things about it, as I mentioned earlier, right? And in this video, we'll explore a few statistics about sequences, and there are other examples that you can play with, right? You can, the length, we have already explored this. We have explored a number of, state changes, the transitions, and we have talked about Shannon's entropy or normalized entropy and turbulence. And there's some other statistics such as complexity index we didn't talk about, but everything. But this is just to demonstrate that TriMiner provides you convenient functions to derive those statistics for the sequences you have. And with all the information, you can feed that into this function, right? This is even better because you just call this function, you let the function know this is the data you want to analyze, and then you put all the statistics you want from TriMiner, including the length, the transitions, entropy, complexity, turbulence, and it returns you a table or a data frame that has all the statistics that maps onto each sequence you have, right? So using this, again, you can go further than this by, for example, looking at how the sequences are different, or you can add or join this data set or this statistic data set you have here with some additional data you have about the player, about their identity, their experience with game in this case, or with some learning outcomes you care about, and start to answer some question that can be answered using this rich sequential data, sequential information you have been analyzed, and merge that with some other data set that describes learning outcomes or the player to answer a question that's more inferential, or it could be causal in terms of if you're provided with a theory about how different factors are informing each other or causing each other in this context, right? So, but for this video, the purpose is we have demonstrated that you can start to do exploratory analysis about sequences. You can plot the sequences in different ways that provides you different insights, provides you different entry point in terms of going further in analyzing your data. In the same time, you can easily derive descriptive statistics about the sequences that can allow you to go further in answering a question that can maybe will leverage additional data coming from your context. With that, I want to thank you for your attention, and I will see you in the next video.